So this exercise related to the topic 1 of unit 2, that is the chemical energetics and the bond enthalpy. The first 16 questions I have already solved, so I will share that recording with you, and we will solve 16 onward. You can also use a chat to state the answer. The chemical energetics and the bond enthalpy questions. The enthalpy or energy diagram is there for the reaction. So as you can see, the reactants have low energy and the product is having the high energy, because the reactant form a product. So X is actually representing a reactant and Y is representing a product. And reactant have low energy and the product is having high energy. So what kind of reaction? So this will be an endothermic reaction, because in endothermic reaction, the reactant absorb energy and then they will form a product. So X is representing the reactant and Y is representing a product. The reaction is endothermic. So C will be the right answer. The next question, the bond energies are given. The table is there. What is the approximate enthalpy change in kilojoule for this reaction? So what simply we have to do, we have to find the bond breaking energy and we have the bond forming energy. So bond breaking energy minus bond forming energy is equals to the enthalpy change of this reaction. So whenever bond energies are given, bond breaking minus bond forming. So bond breaking energy, we have 1, 2, 3, 4. So 4 CH bonds are there. Each CH bond is 430. So it will be 4 multiplied by 430. Then we have carbon-carbon double bond. So carbon-carbon double bond. So this will be 612. Then we have bromine single bond. That is 193. So this will give us a bond breaking energy. About the bond forming energy, the product side is the bond forming. So 1, 2, 3, and 4 CH bonds are there. So this will be 413 times 4. Plus, we have carbon-carbon single bond. As you can see, 347. And then we have bromine, carbon-bromine bonds are there, CBr bond. 1 and 2, like CBr bonds are there. So this will be 2 into 290. So reactant side is the bond breaking side. What is the sum of these all? The bond breaking 413 into 4 plus 612 plus 193. What's the total bond breaking energy? So the final answer, when you take a difference, bond breaking minus bond forming, it's minus 122. Okay. So B will be the right answer. So the idea is bond breaking minus bond forming give us enthalpy change. Next, some energy changes are involved in a Born-Haber cycle. So in Born-Haber cycle, normally we use it to work out the enthalpy change or lattice energy. Electron affinity, lattice energy. Affinity means when electron is added. Lattice energy means when ions will form a compound. Atomization means when element in any other state form atoms in a gaseous state. An element form an atom we call atomization. And standard enthalpy change of formation means when element will form a compound. So which enthalpy or energy change is represented? Here you can see potassium solid become potassium gas. So when atom, so potassium atom is already there, the element, and it form a compound. It form atom in the gaseous state. So when we get atom in the gaseous state, what does it mean? It means this is standard enthalpy change of atomization. So This one, potassium solid turned into potassium gas, so this changes atomization. So atomization is option C, that's why it will be C. Then which enthalpy change or energy change represent? Here you can see element like potassium element and chlorine element form a compound. So when elements are forming a compound, 1 mole of a compound. So what is this in energy change? That is a formation. So which option formation is there? We have for standard enthalpy of formation D. That's why it will be D. And then which enthalpy or energy change represent? Here a chlorine in a molecule in a gaseous state turned into chlorine atom. So this is also atomization. So that is also C. In question 20, consider the following data. Calculate the enthalpy change in the for the following reaction like carbon plus oxygen gives carbon monoxide. You can solve such questions by using a simultaneous equations as well. Like you can just consider them as a simultaneous equation. So we have three different equations and we want carbon and oxygen to be in the reactant and we want carbon monoxide as a product. So what we can do here, like we can solve this as a simultaneous equation. For the first equation, carbon plus oxygen give carbon dioxide. Like if we have carbon plus oxygen give carbon dioxide. So in the equation, we don't want lead. In the equation, we don't want lead or we don't want carbon monoxide. So basically, we want to cancel out carbon monoxide. We have carbon monoxide, like we don't want carbon dioxide. So first, what we can do, if I number these equation like 1, 2, and 3, I want to remove lead and lead oxide. So how I can remove lead or lead oxide from the and lead oxide from this? So if I add these two equations, like if I add 2 and 3. So if I add 2 and 3, because lead oxide here on the right hand side, here on the left, so they can cancel out. When two reagents which are common, they are in opposite side, we add the two equation. If they are on the same side, we subtract the two equation to cancel out them. And lead will cancel with lead. So what when we add these two equations, like after adding 2 and 3, what we are left with? We are left with carbon monoxide, this carbon monoxide. We are left with half oxygen and it gives carbon dioxide. And when we add these two equations, 200, because we are adding it, so 217, like minus 217 plus and then minus 66. So that will come out as minus 283. So this is by adding 2 and 3. That's a result. Then this is the first equation in which carbon plus oxygen gives carbon dioxide. And the energy change is minus 394. Now what we want, we don't want carbon dioxide because in our final equation, there is no carbon dioxide. So what we can do, we can subtract, because the carbon dioxide is on the same side. So in that case, we subtract the two equations. So when we subtract the two equations, this will be minus, this will be minus, this will be plus. This will be also minus. And this will be plus. So this carbon dioxide, it's like a mathematical equation. Carbon dioxide cancel with carbon dioxide. Here we have carbon monoxide, half oxygen plus 1 oxygen. So minus half oxygen is there, minus C. So if this minus half oxygen minus C, it will go other side. So it will become C plus half oxygen. Like here we have So carbon monoxide is equals to C plus half oxygen. And when we simplify, this is giving us plus 111. So for carbon monoxide to convert into carbon and oxygen, it's plus 111. But our equation is opposite. So what will be the energy change for the opposite equation? So it will be minus 111. That's why B will be the right answer for this. Then in question 21, which of the following enthalpy change cannot be measured directly? For endothermic reactions, we cannot measure the enthalpy change directly if a reaction is endothermic. So combustion is always exothermic. Like this will be exo because when something burn, it release energy, so we can measure the energy. Here, formation of carbon dioxide is basically burning of a fuel that is also exo. Combustion of carbon monoxide is also exo. So means obviously this will be endo formation and then this cannot be measured directly. Because exothermic reactions, reactant forming a product, releasing energy. So we just measure the amount of energy released by using the water and work out how much enthalpy change, what is the enthalpy change of a reaction. So endothermic reactions we cannot measure directly because we don't know how much energy is needed to completely change the reactant into product. That's why. So it is difficult to find the enthalpy change or energy change when the heat is supplied. The standard enthalpy change of formations are given. So remember, whenever a formation is given, what we add a link, the element. Always remember. An element will form the reactant or element directly form a product or element form reactant and reactant form a product. So what are the elements here? The elements here we have carbon, two carbon atom in a solid state. We have total 4 plus 2, 6 hydrogen, so 3H2 in a gaseous state. When element form a, here hydrogen is not formed because before and after it's an element formation is always zero. So this is the formation of C2H4. This is the formation of, and 1 mole is formed, so that's a formation of C2H6. And this is the enthalpy change. So according to Hess law, the overall energy change does not depends on the route. So this is the start of the cycle where two arrows are pointing in, that is end of cycle. So if we follow route 1 or we follow route 2, the overall energy change does not depend on the route. So we can say the standard enthalpy change of formation of C2H4 plus the enthalpy change of this reaction is equals to standard enthalpy change of formation of C2H6. Or if we need this, the enthalpy change is equals to formation of the product, the total formation of product minus formation of reactant. And that we discussed, if formations are given, it is always enthalpy change of a product minus the reactant. So it will be product is formation is given, the reactant formation is given, product is given. So we just substitute minus 84.7 minus and then 52.2. When we simplify, it will be 136.9 negative. So whenever formation is given, you will add a link element. If combustion is given, you will write a combustion product for both reactant and product, and the arrows must point outwards. Which of the following equation represent a reaction for which enthalpy change is a standard enthalpy change of formation? So formation means when element form a compound, that is called a formation. And we should get the standard state. This cannot be because ions are there. This element form a compound. Here, it's not element, not here elements are there in the reactant forming a product. That's why it is a formation. Considering the following bond enthalpies, we need the enthalpy change of this reaction. So carbon monoxide bond energy is 1077. Oxygen, look, one mole of oxygen is 498. So this is 498, 1 mole. But there is a half mole, so it will be divided by 2. That is the bond breaking energy. And bond forming energy, because in carbon dioxide, one bond is 805. But in carbon dioxide, there are two double bonds, so this will be twice of 805. So 1 mole of double bond is 498. Half mole of double bond, that will be half of it. So this will be the bond breaking energy and this is the bond forming energy. We just take a difference between the bond breaking and the bond forming to get the enthalpy change. So minus 284, or A will be the right answer. In question 25, in endothermic reaction and aqueous solution, which of the following is correct? When endothermic reaction occur, the heat energy is being absorbed. So it will feel colder, the surrounding temperature of the mixture decreases because the reactant particle absorb energy. What is the sign for enthalpy change? It will always be positive. So C will be the right answer. Here, we just have to mention what is the equation. So how to work out whenever you have the cycle is given, where the two arrows are pointing out, that is the start of the cycle. And where the two arrows are pointing in, that is end of cycle. So if we follow route 1 or we follow route 2, the overall energy change is independent of the route. So delta HR plus delta H2 is equals to delta H1. If I need delta HR, it will be delta H1 minus delta H2. So delta H1 minus delta H2. So for this one, B will be the right answer. In question 27, when 10 cm cube of 2 mole per dm cube hydrochloric acid reacted with 10 cm cube of 2 mole per dm cube sodium hydroxide, the energy change, delta H, the energy change, or sorry, temperature change is delta T. When the reaction is repeated with 50 cm cube of each solution, what will happen to delta H? Look, remember the energy change E is equals to Cm delta T. That is a formula which relate specific heat is constant. So temperature change is directly proportional to number of moles energy released, and temperature change is inversely proportional to the mass or the volume of the solution. First, initially, how much total volume of the solution? 10 plus 10, 20. And then we took 50 cm cube of each, so 100. So means when we work out, so 10, like first it was 20 and 20 become 100. So how many times it has changed? It has changed by factor 5. So if the mass or the volume of solution is multiplied by 5, the temperature change will decrease by 5. That is one thing. But we change both solutions. So what happened to the temperature change is directly proportional to moles. When you work out the moles here, like this will be 10 divided by 1000, so 0.01 into 2. So this will be 0.02 and this also 0.02. So total moles are 0.04, or moles of each reactant, because we don't need for total, we need for one of them, as both of them are limiting, so we can take any one of them. So originally moles are 0.02, but when we took 50 cm cube of the same concentration, so it will be 0.05 multiplied by 2, which is equals to 0.01. 0.1, no, not 0.01 because multiplied by 5. So 0.1. So what happened to the moles? It was 0.02 in the beginning for any of the reagent, as both of them are used up. So it turned into 0.1. If the number of moles are multiplied by 5, temperature change will also be multiplied by 5. So due to change in the volume, the temperature change is divided by 5. Due to change in the mole of the limiting reagent is multiplied by 5. So what is the overall change in the temperature? So it won't change. So delta T will be like, it will be same temperature change for the first as it was there for the first reaction.